It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
If you have been with us since the beginning of Part 4, you have already built a profound, foundational understanding of deep learning. You know what a multi-layer perceptron is, you understand the role of activation functions, and you have grasped the incredible engine that drives learning, the one-two punch of gradient, descent, and backpropagation. We have established that a neural network is essentially a universal function approximator, capable of learning any relationship between input and output, provided it has enough layers and enough data. However, as we transition into this new section, Part 5, we must address a critical challenge. The general-purpose multi-layer perceptron, or MLP, while theoretically powerful, is profoundly inefficient when dealing with complex, high-dimensional, grid-like data, specifically images. To understand why, let's look at the world around us. How does a self-driving car navigate a four-way stop? How does a medical system analyze an X-ray to spot a subtle tumor? How does your smartphone authenticate your identity simply by looking at your face? The answer to all these questions lies in a specialized, highly efficient neural network architecture called the Convolutional Neural Network, or CNN, and the field of study it powers, computer vision. This episode is our gateway into specialized deep learning architectures. It's where we learn that the shape of the neural network must be tailored to the shape of the data. Our objective today is to systematically deconstruct the CNN, understanding the biological inspiration behind it, recognizing the catastrophic inefficiencies it solved, and exploring the genius concepts of local connectivity and parameter sharing that make machine vision possible. By the end of this hour, you will not just know that machines can see, but how they see, pixel by mathematical pixel. Let us begin with the foundation. What exactly is computer vision? Computer vision is the scientific field of artificial intelligence concerned with enabling computers to derive meaningful information from digital images, videos, and other visual inputs. It is the effort to automate the human visual system. Think about the complexity of human sight. We see a scene, a crowded street corner, a forest, a bookshelf, and instantaneously, without conscious effort, we parse that visual information into objects, depth, motion, identity, and context. A computer must perform the same feat, but it starts with a grid of numbers. When a machine sees an image, it is not perceiving the smooth colors and continuous textures that we do. It is receiving a grid, a massive matrix of numerical values. For a grayscale image, each pixel is represented by a single number, usually between 0 and 255. For a color image, it gets more complex. We typically use the red, green, blue, or RGB color model. This means that for every single point in the image, every pixel, there are 3 values: one intensity value for red, one for green, and one for blue. Therefore, a standard color image is not a single two-dimensional matrix, but a three-dimensional tensor: height, width, and depth, where the depth is usually the 3 color channels. The core tasks of computer vision are varied and increasingly sophisticated. The most fundamental task is image classification, answering the question, what is the main subject in this image? Is it a cat, a dog, or a truck? Moving beyond classification, we have object localization, which identifies the main subject and draws a bounding box around it. It answers not just what, but where. Object detection takes this a step further by identifying multiple objects in the same image, perhaps a pedestrian, a bicycle, and a traffic light, and drawing bounding boxes around each. Finally, we have semantic segmentation, which is perhaps the closest analog to truly understanding a scene. In segmentation, the goal is to label every single pixel in the image with its corresponding class. A self-driving car uses semantic segmentation to paint the road blue, the sidewalk red, the pedestrian green, and the sky yellow, allowing it to understand the geometry and navigable space of its environment on a pixel-by-pixel level. To achieve any of these sophisticated tasks, the AI must first conquer a massive computational hurdle that the general-purpose MLP simply cannot overcome, and this leads us directly to the problem with MLPs and the curse of dimensionality. Recall the structure of an MLP. Every single neuron in one layer is connected to every single neuron in the next layer. This is why we call it fully connected. This design is elegant for tabular data or smaller, well-defined feature sets. However, consider a relatively small image, say 200 pixels by 200 pixels. At 3 color channels per pixel, this image has 200 times 200 times 3, or 120,000 input features. If we attempted to feed this single image into the first hidden layer of an MLP, and if that hidden layer contained, say, a modest 1,000 neurons, each of those 1,000 neurons would need to have 120,000 weights connecting back to the input layer, plus a single bias term. One hidden layer, 1,000 neurons. That's 1,000 times 120,000. 120 million parameters just for the connection between the input and the first hidden layer. If the network had several such layers, the total number of parameters would skyrocket into the hundreds of millions, if not billions, even for this small image. This enormous number of weights creates two fundamental catastrophic problems for image processing. The first is, obviously, computational expense. A network with billions of parameters is incredibly slow to train, requires massive amounts of memory, and needs petabytes of data just to begin making sense of the connections. The second problem is the critical concept of overfitting and the lack of invariance. In the context of images, invariance refers to the network's ability to recognize an object regardless of minor changes in its appearance. For instance, if you show a child a picture of a cat, they can recognize it whether the cat is in the top left or the bottom right, whether it's slightly rotated or whether the lighting is poor. The child's brain has translational invariance. An MLP, being fully connected, is terrible at this. If the network learns to recognize a specific pattern, say, a vertical edge at pixel location X, Y, and then that same exact pattern appears at location X plus 10, Y plus 10, the network treats it as an entirely new feature because the weights connecting to the new location are different. This lack of inherent spatial awareness means the MLP must be retrained to recognize the pattern in every single possible location, orientation, and size, requiring exponentially more data and leading to massive overfitting on specific image locations. It's like having to teach a network a new language every time the cat shifts its position slightly on the couch. This is the problem the convolutional neural network was explicitly designed to solve. To understand the solution, we must first turn our attention to inspiration and architecture. The CNN is one of the most brilliant examples of engineering borrowing from biology. Its foundational concepts were inspired by Nobel Prize-winning work on the visual cortex of mammals. In the 1950s and 60s, neurophysiologists David Hubel and Torsten Wiesel conducted seminal experiments that mapped the function of neurons in the visual cortex of cats and monkeys. Their work revealed that the visual processing system is not a chaotic mess of interconnected neurons, but a highly structured, hierarchical system. They found that individual neurons in the primary visual cortex did not respond to general light across the entire visual field. Instead, they had what are called local receptive fields. A specific neuron would only fire when a stimulus, say, a vertical line or a diagonal edge, appeared in a very specific small area of the animal's vision. They categorized these into two types: simple cells, which responded to edges at a specific orientation and location, and complex cells, which responded to the same orientation but were more forgiving about the exact location, demonstrating a degree of translational invariance. As signals progressed deeper into the brain, through successive layers of neurons, these simple, localized features, edges and corners, were combined to create more complex feature detectors. Like those for specific shapes, textures, or moving objects, this insight, the idea of hierarchical feature detection based on local specialized components, became the blueprint for the convolutional neural network. The CNN takes this biological model and implements it with two core mathematical innovations that directly address the parameter explosion and the lack of invariance that plagued MLPs. These concepts are local receptive fields, which we can call local connectivity in the neural network context, and parameter sharing, which is the mechanism that defines the convolution operation. Let us dive deep into the first mechanism, local connectivity. In a CNN, the neurons in a convolutional layer are not connected to all the pixels in the input image. They are only connected to a small local region of that image. For instance, a common setup uses a 3x3 area, or perhaps a 5x5 area. This small region is the neuron's local receptive field. Imagine our 200x200 image. Instead of 120,000 inputs, a neuron in the first convolutional layer might only receive input from a small 3x3 patch of pixels. That's 9 pixels times 3 color channels, or 27 inputs. 27 inputs instead of 120,000. The parameter count immediately collapses to a manageable number. This design assumes, correctly, that most patterns in an image, such as an edge or a corner, are local patterns, meaning they can be detected by looking only at a small region. To detect a vertical line, you don't need to look at the other side of the image. Now we introduce the second and arguably more ingenious concept, parameter sharing. In an MLP, if you wanted to detect vertical lines in two different places in the image, you would need two completely different sets of weights, two separate neurons, each learning its own 120,000 parameters to achieve the same goal. In a CNN, we introduce a concept called the filter or the kernel. This filter is simply a small two-dimensional matrix of weights, say, a 3x3 matrix. This matrix is the same size as the local receptive field we just discussed. This filter is essentially a tiny specialized pattern detector. Crucially, the same exact set of weights, the same filter, is systematically applied to every single local receptive field across the entire image. This is parameter sharing. This single filter learns to detect one specific type of local feature, such as a horizontal edge, and then we assume that if a horizontal edge is important in one part of the image, the same mathematical definition of a horizontal edge will be important everywhere else in the image. Why should the weights for detecting a horizontal edge on the left be different from the weights for detecting a horizontal edge on the right? They shouldn't be. By sharing the weights, we drastically reduce the total number of parameters and simultaneously grant the network that critical property we discussed earlier, translational invariance. If the pattern shifts, the network can still recognize it because it uses the same detection mechanism. The mathematical operation that implements this local connectivity and parameter sharing is called convolution. This is the heart of the CNN, so we must explore it in detail. Think of the convolution operation as a sliding window or a mathematical magnifying glass. You have your input image and you have your filter, which is our small matrix of shared weights. The process begins by placing the filter over the first receptive field, for example, the top left 3x3 patch of the input image. Next, we perform an element-wise multiplication between the 9 numbers in the filter and the corresponding 9 numbers in that patch of the input image. Then, we sum up all those 9 multiplication results. And finally, we add the bias term associated with that filter. The single number resulting from this summation is the output for that position. This single output number represents how strongly the feature that the filter is designed to detect, say, a diagonal line, was present in that specific patch of the image. A high positive number means the feature was strongly detected. A negative number might mean the opposite pattern was detected, and a number close to 0 means the feature was not present in that region. Once the calculation for that first patch is complete, the filter slides over to the next patch, perhaps 1 or 2 pixels over, depending on what we call the stride. The stride dictates how many pixels the filter jumps between applications. The filter repeats this process, systematically sweeping across the entire width and height of the input image. For every position the filter lands on, it calculates one output value. The resulting two-dimensional matrix of all these output values is called the feature map, or the activation map. This feature map is essentially a distilled representation of the input image, highlighting the presence and location of the specific feature the filter was looking for. This is the core of the convolutional layer. An important point is that a convolutional layer does not use just one filter. If it did, it would only be looking for one type of feature, like vertical edges. Instead, a typical convolutional layer might employ 32, 64, or 128 different filters. Each filter is initialized with different random weights, and, through backpropagation and gradient descent, each filter learns to detect a different local feature. One filter might specialize in detecting horizontal lines, another in detecting curved corners, and a third in detecting a specific color gradient. Therefore, the output of a single convolutional layer is not just one feature map, but a stack of feature maps, one for every filter used in that layer. This output stack then serves as the input for the next layer in the network. Now, let's stop and correct a common misconception right here, something that trips up even experienced students: the relationship between the filter, the feature map, and what the network actually sees. The misconception is that the network learns features like eyes or wheels immediately. The reality is that the features learned in the early layers, the first or second convolutional layers, are completely abstract to us. They are not human recognizable concepts. They are mathematical patterns, simple edges, texture variations, and color blobs. We can visualize what a filter has learned by looking at which input patterns maximize its activation. But those patterns are usually complex, mathematical combinations of pixels that are rarely obvious human-defined shapes. The true magic of the CNN comes from the third key concept in our journey: hierarchical feature learning. The power isn't in a single layer, it's in stacking many layers. Imagine you are looking at a complex piece of machinery, say, an internal combustion engine. You don't see it all at once, you decompose it. The lowest level of understanding involves recognizing the raw components, the nuts, the bolts, the metal surfaces. The next level involves understanding how those components combine into functional units: a piston, a connecting rod, a valve. The highest level is recognizing how those functional units combine to form the engine system itself. A CNN works exactly like this, learning in a hierarchy. The first convolutional layer detects the most granular, simple features: horizontal edges, vertical edges, specific color transitions. These are the nuts and bolts. The second convolutional layer takes the feature maps from the first layer as its input. Remember, these feature maps indicate where the simple features are located. The second layer's filters look for patterns among those simple features. For instance, a filter in the second layer might learn that when a horizontal line feature and two vertical line features are positioned just so, that combination signifies a corner. It learns to recognize geometric primitives by combining the outputs of the previous layer. The deeper we go, into the third, fourth, and fifth convolutional layers, the more complex and abstract the learned features become. The deeper filters combine corners and circles into recognizable shapes, such as eyes, noses, or wheel arches. The final deep layers of the convolutional stack are looking for the combination of these complex features to identify entire objects: a face, a car, or an animal. This systematic, hierarchical combination of features is why CNNs are so robust and effective. They automatically learn the best representation of the visual data needed for the final task. Before the feature maps are passed to the final decision-making part of the network, there is one more crucial component often interspersed between the convolutional layers: the pooling layer. The purpose of pooling is twofold. First, to drastically reduce the size, the dimensionality of the feature maps, and second, to make the learned features even more robust to small shifts or distortions in the input image. Let's stick with our analogy of the pattern detector. Suppose a filter in a convolutional layer detects a vertical edge in a 3x3 patch. It produces a strong positive activation value in that specific cell of the feature map. Now, suppose the vertical edge shifts 1 pixel to the right in the original image. The previous convolutional layer will still detect the edge, but the strong activation will now appear 1 cell to the right in the feature map. For the high-level task of classification, the network doesn't necessarily need to know the exact pixel location of the edge. It only needs to know that the edge exists in that general area. Pooling abstracts this precise positional information away. The most common type is max pooling. Max pooling operates much like convolution, using a sliding window, typically a 2x2 or 3x3 window, that strides across the feature map. Instead of calculating a weighted sum, the max pooling layer simply takes the maximum value within that window and uses that maximum value as the output for that region. If we use a 2x2 window with a stride of 2, we are effectively reducing the height and width of the feature map by half. For instance, a 100x100 feature map becomes a 50x50 feature map. We are condensing 4 values into one single value, retaining only the strongest signal, the highest activation from that local area. The intuition behind max pooling is elegant. If the filter strongly detected a feature somewhere in that 2x2 region, we record that strong detection signal and discard the less important activations. By preserving only the strongest signal, max pooling achieves 2 things. It reduces the total number of computations for the subsequent layers, and it increases the network's tolerance to slight shifts, translational invariance, because a slight movement of the feature within the pooling window still results in the same max-pooled output. So now we can define the full, canonical architecture of a CNN. it is a sequence of stages. We start with the input image. This is followed by a repeating sequence of a convolutional layer, an activation function, typically ReLU, which we discussed previously, and a pooling layer. This repeating block is where the feature extraction happens. The network goes from low-level features to high-level features. After several of these blocks, the feature maps are now greatly reduced in size, but highly rich in semantic information. They represent high-level concepts like, is this part of an eye, or is this the shape of a wheel? The resulting 3D tensor of high-level feature maps is then flattened, meaning it is unrolled into a single, long vector. This vector is fed into a traditional, fully connected multi-layer perceptron. The purpose of this final MLP stage is to take the learned features, the output of the convolutional stack, and use them to perform the final classification, regression, or decision-making task. For example, if the network is classifying images of cats and dogs, the convolutional layers extract features like fur texture, ear shape, and snout dimensions. The final MLP takes this comprehensive feature vector and determines, based on all those high-level signals, whether the probability of cat or dog is higher. This combination of specialized, feature-extracting convolutional layers and general-purpose, decision-making fully connected layers is the blueprint for virtually every successful computer vision system over the last decade. The true breakthrough moment for the CNN came around 2012, marking a watershed moment in the history of AI, and this transition leads us to real-world applications and the ImageNet revolution. Before 2012, the state-of-the-art in computer vision relied heavily on manual feature engineering. Researchers would spend years trying to define mathematical algorithms, not learned but hand-coded, to recognize things like edges, corners, and color histograms. This was difficult, brittle, and highly non-scalable. Then came the ImageNet Large-Scale Visual Recognition Challenge, or ILSVRC, and the AlexNet architecture. ImageNet is a massive dataset containing millions of labeled images across thousands of categories. The challenge was to classify these images with the lowest error rate. In 2012, a team led by Alex Krzyzewski and his supervisors Jeffrey Hinton and Ilya Sutskever deployed a deep CNN architecture, later known as AlexNet. It achieved an error rate that was dramatically lower than the best competitor, who used traditional, non-deep learning methods. This moment, often called the ImageNet moment, proved conclusively that deep learning, and specifically the CNN architecture, could learn better, more robust and more sophisticated features automatically from raw pixel data than any human expert could ever hand-engineer. This success sparked a revolution that drove the error rate down year after year, with increasingly deeper and more creative CNN architectures, VGGNet, GoogleNet, and ResNet, achieving near-human and then superhuman performance on complex visual tasks. Today, CNNs are ubiquitous, powering essential aspects of our digital lives. First, consider the field of self-driving cars. These vehicles rely heavily on object detection and semantic segmentation powered by CNNs. The CNN must operate in real time, analyzing live video streams to detect pedestrians, other vehicles, lane markers, and traffic signs. Sophisticated CNN models like YOLO, which stands for You Only Look Once, can process dozens of frames per second, drawing bounding boxes around every relevant object. In medicine, CNNs are revolutionizing diagnostics. They are trained on millions of medical images, X-rays, CT scans, MRIs, and microscopic images of tissue slides. a CNN can be trained to spot microscopic indicators of disease, such as subtle lesions in mammograms or early signs of diabetic retinopathy in retinal scans, often with speed and accuracy that matches or exceeds human specialists. The network identifies those high-level, hierarchical features that correlate strongly with a specific diagnosis. Even something as mundane as your smartphone camera uses CNNs. Portrait mode, which artfully blurs the background while keeping the subject sharp, uses a CNN to perform foreground-background semantic segmentation. It literally has to classify every pixel as person or background before applying the aesthetic blur. The sheer adaptability of the CNN architecture stems from its ability to solve the fundamental problem of visual representation. It automatically transforms raw, high-dimensional, fragile pixel data into low-dimensional, robust, and semantically meaningful feature vectors that are ready for final classification. This robustness is also the key to our next advanced insight, the power of transfer learning. In AI, building a massive, highly accurate deep learning model from scratch is a formidable task. It requires extraordinary computational resources and critically gargantuan amounts of labeled data. For many specific tasks, say, classifying rare butterfly species or identifying specific equipment failures in machinery, that data simply doesn't exist in the necessary volume. This is where the concept of transfer learning becomes a lifesaver, especially with CNNs. Transfer learning relies on a simple, yet profound observation about the hierarchy of features we discussed. The earliest layers of any CNN, regardless of whether it's trained to recognize cats, cars, or cancerous cells, learn essentially the same fundamental things. They all learn to detect edges, corners, blobs of color, and texture gradients. These features are universal to all images. Only the deeper layers, the ones close to the final classification layer, learn the highly specific features required for the target task, the difference between a Labrador and a poodle, or the subtle shape of a tumor. Transfer learning exploits this shared knowledge. Instead of starting from scratch, a researcher will take a pre-trained CNN, say, a ResNet model, that has already been trained on the entire 14 million image ImageNet database. This model has already learned those foundational, generalized features across its first layers. The researcher then freezes the weights of these early, feature-extracting convolutional layers, locking in the general image understanding they already possess. They then replace the final, fully connected classification layer with a new one designed for their specific, small dataset task, say, classifying 5 types of butterfly. They then train only the new final layer, or maybe allow the last few convolutional layers to fine-tune. Since the hard work of learning universal visual features is already done, the model requires vastly less data and computational time to achieve high accuracy on the new, specific task. The knowledge of general visual patterns is successfully transferred from the general domain of ImageNet to the specific domain of butterfly classification. This is one of the most practical and important concepts in modern deep learning deployment, and it is uniquely suited to the CNN's hierarchical structure. Another advanced insight reveals the boundary of the CNN's utility. While we have focused on images, the core convolution operation, the sliding window and weighted sum, is essentially a way to process local, grid-like patterns. This means CNNs can be adapted beyond two-dimensional images. For example, when dealing with 3D data, such as a volumetric CT scan of a patient's chest, we can use 3D convolution, where the filter is a small cube of weights that slides across the volume in 3 dimensions, height, width, and depth. Furthermore, CNNs can be used to analyze 1D data, such as time series or audio signals. Here, the input is a single long vector, and the convolutional filter is simply a short 1D array of weights that slides across the time sequence. This is highly effective in signal processing and certain types of natural language processing tasks. Before the age of the transformer, the principle remains the same. The architecture is specialized to find local patterns in a structured input. The success of the CNN cemented the principle that architecture follows data. For spatial data, for grid-like data, the convolutional neural network is mathematically and computationally the superior choice. However, as we move through our curriculum, we must also recognize the limitations of the CNN, and this limitation will provide our crucial link to the next episode. Think about the convolution operation again. When the filter slides across the image, it performs its calculation, creates an activation, and moves on. At no point does the filter at position x, y have explicit knowledge of what happened at the calculation at position x minus 10, y minus 20. There is no inherent memory or sequential awareness in the structure of the CNN itself. This lack of explicit sequential memory is not a problem for images. When classifying an image, all the relevant information, the cat's ears, eyes, and fur, are present simultaneously in the input grid. The spatial arrangement matters, but the order of observation does not. But what if the data is inherently sequential? What if the meaning of the current input depends critically on a long chain of previous inputs? This is the case with spoken language, text, financial time series, or DNA sequences. When we read a sentence, the meaning of the word bank depends entirely on whether the previous words were river or financial. A standard CNN, which is designed to identify spatial patterns simultaneously, struggles mightily when the data must be processed over time, where context from the past must influence the processing of the present. The CNN revolutionized how machines see the static world. But the vast complexity of the digital world is not static, it is often sequential. To master AI literacy, we must now build an architecture that remembers the past and processes information with a sense of time. In conclusion, the journey from the fully connected, parameter-heavy multi-layer perceptron to the specialized, efficient convolutional neural network is a powerful lesson in architectural genius. The CNN solved the visual representation problem by mimicking the hierarchical structure of the human visual cortex, moving from local, simple feature detectors, the kernels, to complex, semantically meaningful feature maps. Through the powerful, parameter-reducing mechanisms of local connectivity and weight sharing, the CNN proved that deep learning could conquer the high dimensionality of visual data. It demonstrated the overwhelming superiority of automatically learned features over brittle, hand-engineered ones, driving the explosion of applications from self-driving cars to medical diagnostics. We have learned that AI vision is not passive looking, but an active, systematic, mathematical search for patterns, built upon a hierarchy of increasingly abstract feature combinations. But the CNN's focus on local spatial invariance leaves a critical hole in our AI toolkit: the ability to handle data where the sequence matters, where context must be carried forward through time. That necessary capability, the ability for a neural network to remember and process sequences, is what we will explore in our next session as we delve into the world of recurrent neural networks, or RNNs.
You've been listening to AI Deconstructed, Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.